Greetings and welcome to the Advanced Hydronics Incorporated Ground Source Heat Pump and Air Source Heat Pumps Basics class. I am Mark Etherton and producing this video from the depths of my COVID-19 fortress. I have black lights in every corner and having to wear sunglasses because it's hurting my eyes. Anyway, thank you for joining us and get ready to drink from a fire hose. What is a heat pump? Heat pumps are devices for converting low temperature heat into higher temperature heat. The low temperature heat is gathered from some material called typically the source, and then the concentrated heat is then released into another material commonly known as the sink. The refrigeration cycle is the basis of operation of all vapor compression heat pumps. During this cycle, a chemical compound called a refrigerant circulates around a closed-loop piping passing through all major components of the heat pump. These major components are named based on how they affect the refrigerant passing through them. They are as follows. There will be an evaporator, a compressor, a condenser, and a thermal expansion valve. The primary mover of this gas is the compressor, which is item 2 listed in this picture. Immediately after the compressor, the high temperature, high pressure gas vapor then travels into the condenser. The condenser is where the thermal energy is released to the actual load. The load media could be air in the case of an air distribution system. If it's hydronics, it will be water. As the name implies, the condenser's job is to convert this high pressure vapor into a liquid. Once the medium temperature, high pressure liquid hits the thermal expansion valve, the pressure differential causes the fluid to become extremely low temperature. At this point, the low temperature, low pressure liquid enters the evaporator. As the name implies, it's looking for heat, and once it finds heat, the fluid will evaporate and become a vapor again. The source media can be air in the case of an air source heat pump, or the ground, or waste heat recovery, or anything that actually has a thermal energy potential that is greater than the temperature of the refrigerant. Remember, heat flows from hot to cold always. At this point, the medium temperature, low pressure vapor is then returned to the compressor for compression. And this completes the simple refrigerant loop cycle for heat transfer. In this particular case, it's being shown as a heating need. If there was a need for also a cooling need, there will be a reversing valve that will flip-flop the evaporator and the condenser so that heat can be transferred from point A to point B or from point B to point A. That will come in a future slide. Per this graphic, the overall energy transfer, which is essentially what this system does, is Q1, which is the low temperature heat absorbed from the heat source, plus Q2, which is the parasitic cost of operation of the compressor. All of its electrical energy is converted to heat and is added to the refrigerant, so it's Q1 plus Q2 equals the output temperature, which is Q3, hence the coefficients of performance of 3 to 1. Heat pumps are categorized based on the media from which they extract heat, as well as the media to which they dissipate heat. The most common categories are air-to-air heat pumps, which have been around for quite a while, air-to-water heat pumps, which are relatively new to this market coming from the European side, water-to-air heat pumps, which again are a new European installation, and water-to-water heat pumps, which we are most familiar with and have been around for about 50 years. As previously mentioned, with the introduction of a reversing valve, the evaporator and the condenser can be flip-flopped, meaning that you can extract heat from the ground and pump it into the house, or you can extract heat out of the house and pump it into the ground in the case of a water source heat pump. In the case of an air helium type of heat pump, it's essentially the same thing. It's just that you're dealing with a lot less mass-intensive material for the heat source as well as the heat sink. This depiction shows an air source heat pump. This is an air-to-air installation. Essentially, the ambient air outside is introduced into the compressor condenser evaporator package, and you can either extract heat from the air and pump it into the house, or you can extract heat out of the house and pump it out into the ambient air outside. Note the location of this outdoor unit in relationship to the drip line of the roof. That's an area that a person needs to be cautious of, otherwise you will get excessive snow loading onto your heat source heat rejection unit, and the system will not work as well as it's supposed to. Follow the manufacturer's recommendations. Depicted is a typical outdoor unit which contains the compressor, the condenser, and an evaporator. This is the primary heat source as well as the means of heat rejection for this system. Depicted in Figure 1-7 is the typical refrigerant path flow. From the compressor, in the case of heating, it goes from the compressor to the condenser. From the condenser, it gives up the heat to the space, and then the fluid is then sent to the evaporator, where it extracts additional heat out of the ambient air outside. In the case of heat rejection, the evaporator and the condenser are flip-flopped through the three-way reversing valve. In the case of an air-to-water heat pump system, essentially the compressor-condenser package is outside, and a refrigeration line passes between the compressor-condenser evaporator package and a flat plate heat exchanger on the inside of the building. Depicted in Figure 1-11 is a water-to-air heat pump system. Essentially, the heat source, in the case of heating, would be a ground source heat pump system consisting of vertical boreholes, horizontal loop field, slinky pit, any method of being able to extract that low-grade heat from the earth and transfer it to the air on the inside of the system. In the case of cooling, as depicted on the lower section, the ground source heat pump becomes the sink at that point, and essentially you extract heat out of the air of the conditioned space and pump it into the earth. Figure 1-13 shows a water-to-water heat pump system. The top photo is shown in the heating mode. The bottom photo is shown in the cooling mode. Essentially, there will be two water-to-refrigerant heat exchangers in each module, and again, with the reversing valve, you can flip-flop the evaporator and the condenser and either extract heat out of the earth or the heat source and pump it into the house, or you can pump it out of the house and into your heat sink, which would be your loop field, vertical boreholes, whatever method you have for being able to do this. I should note at this point also that we have a property called Courthouse Square that utilizes water-to-water heat pumps. The heat source in this particular case are condensing boilers, and the heat sink, in order the method of being able to get rid of the heat, is a water-cooled cooling tower on the roof of the building. So these heat pumps are not always necessarily attached to a ground source heat pump system. As it pertains to heat pumps, there are two thermal performance factors that have to be taken into consideration. These indices that describe the heating performance of any heat pump are heating capacity, as listed in BTUs per hour, and the coefficients of performance, which is essentially the ability of this unit to transfer heat from a source to a load, or from a load to a source, and its efficiency in doing that is expressed in terms of kilowatts. In other words, if you move 3 kilowatts of energy with 1 kilowatt of consumption, then your coefficients of performance would be 3-to-1. The cooling capacity of the system is essentially expressed in cooling capacity in BTUs per hour, also expressed as tons. 1 ton of energy transfer in refrigeration is 12,000 BTUs per hour. And the energy efficiency ratio. The reason for the energy efficiency ratio is so that these units in their cooling mode can be compared to conventional air type of cooling systems. And you will note that their energy efficiency ratio is extremely high because the sink always is cool. The problem with conventional air-cooled refrigeration systems for cooling a house is that you are trying to dump heat with hot air into hot air, and the performance when it's extremely hot outside is extremely low. Shown in Figure 2.1 is the heating capacity of a heat pump. The variables are the entering source water temperature from the ground, the loop, slinky field, whatever you happen to have, as well as the entering load water temperature from the actual connected load itself. You will note that the blue line has an 80-degree entering load water temperature, which has a fairly significantly higher ability to be able to put out heat for the same water temperature from the heat source itself. This is important in the designing of the hydronic radiant floor heating system to ensure that in order to retain peak efficiency, the heat medium must be as low a water temperature as possible, typically a source water temperature between 90 and a maximum of 115 degrees Fahrenheit. If the load demands a water supply temperature greater than 115 degrees Fahrenheit, then you will need a two-stage system whereby a boiler will come online to pick up where the heat pump is left off at 115 degrees Fahrenheit. Figure 3-2 shows the average surface temperature for depths of 2 feet, 5 feet, and 8 feet below grade. Obviously, the deeper you go, the warmer the temperature during the winter months, and the better the performance of a ground source heat pump. As it pertains to vertical boreholes, typically from 30 feet to about 200 feet below the surface, the soil temperature is a relatively constant 55 degrees Fahrenheit. These are important factors that ground source heat exchanger designers take into consideration. A horizontal slinky loop that is only 5 to 8 feet deep is not going to perform the same as a vertical borehole that has been drilled to 200 foot deep. Shown in figure 3-5 is an open loop lake loop system. Essentially, the water from the bottom of the lake is pumped up into a flat plate heat exchanger. It goes through a solids separator, which takes any solids, sand, dirt, etc. out of the loop and avoids fouling the heat exchanger. When considering this type of a system, it's important that there be stream flow into and out of the lake that equivals the capacity of demand that the heat pump system is going to provide. Otherwise, you can anticipate turning the whole lake into a large chunk of ice, which is actually okay by design. There's a system up in Granby, Colorado that does this very same thing. Depicted in figure 3.6 is what is commonly known in the industry as a pump and dump. Essentially, a submersible pump is in a well. This is the same water that would be used for potable water applications. Essentially, the water is pumped up through a heat exchanger. The heat exchanger is providing both a heat source as well as a heat sink if the system is in the cooling mode. The disadvantage of this type of system is that most authorities having jurisdiction frown upon its use. They're worried about contamination of the aquifers. It's also important that you check with your state Division of Natural Resources before you employ this type of a system. It is considered illegal in some states. Depicted in figure 3-7 is a single pipe trenched system. Essentially, the excavation is done with a chain trencher, which is capable of giving you a trench that's 6 inches wide and roughly 6 foot deep. A single pipe is laid in the bottom of this trench, and then it is backfilled and compacted. This is what a single pass loop field would look like. It would probably be requiring more than one loop to be able to satisfy the needs. Typically, one loop is capable of handling 1 ton worth of energy transfer, which is 12,000 BTUs. Figure 3-9 shows a two-pipe system. We have one pipe on the bottom of the excavation and another pipe roughly 2 feet above that. Obviously, the soil conditions are going to dictate the heat exchanger's capabilities of transferring BTUs. A sandy or a gravelly type of mixture of soil is going to have very poor conductance versus a system that has tightly bound clays, and moisture also plays a key factor in the ability of these heat exchangers to transfer heat into and out of the loop field. Shown here are some 2-foot excavations, which would have to be done obviously by a backhoe or a track hoe, and essentially you have the opportunity for being able to lay 2 to 4 pipes within this given consideration. Obviously, again, soil conductivity is a key factor, hence the reason that loop fields are designed by certified geosource ground connection heat exchanger designers. The International Ground Source Heat Pump Association is the best resource for this information. This graphic depicts an open pit slinky loop type of system. Essentially, the pit is excavated down to about 6 to 8 foot deep. The tubing is laid out in a slinky pattern, and then it is backfilled. It has been found over the years that the obvious soil conditions and the moisture content of the soil significantly affects the ability of this type of a heat exchanger to be able to transfer heat from the earth to the load or from the load to the earth. A lot of designers have resorted to putting a perforated tremie pipe into the center of all of these loops so that if necessary, they can induce water into the loop field and retain or increase its thermal conductivity. Figure 3-12 shows a typical vertical borehole application. Typically, these wells are between 200 and 300 feet deep, possibly deeper, and essentially they are tubes that are grouted in place. These tubes are filled with their alcohol water solution before they are submerged, and they are hydrostatically tested prior to actually covering the excavation up. The trench on the top is excavated by a backhoe, where all of the plastic tubing is fusion welded, and then eventually the supply and return loop ends up on the inside of the building. The joints on this type of tubing are typically provided by the loop field contractor and are done with polyethylene tubing and are typically a fusion socket weld or a fusion butt weld type of joint. Shown in figure 3-21 is a remote manifold. Each one of the branch circuits would be connected to a vertical borehole drill. This type of a system is advantageous from the standpoint of being able to isolate an individual loop if you suspect a leak, or also provide you with the ability to be able to purge one loop circuit at a given point in time. This manifold could be located on the inside of the mechanical room, or it may be located outside underground in a pit that receives all of the supply and return lines from all of the vertical borehole drills. Graphic 3-28 shows a configuration for the pumping station. Most of these geo-pumping stations are a push-pull type of arrangement with a valve arrangement in the bottom of the unit that basically allows for high-capacity purging. This requires the use of a separate large high-capacity pump to be able to get adequate velocity to ensure that you get air entrainment and then the air brought back to your fill system. Figure 3-29 shows another method of being able to provide circulation for the ground source loop. Note in this installation that there is an expansion tank, an air separator, and a dirt separator. Although these are not common in most ground source heat pump systems, if we are responsible for its design, it is strongly recommended that these components be included as a part of the bid package. Figure 6-4 shows all of the components necessary for a water-to-water radiant heating and hydronic fan coil cooling system. The red and blue tank on the top is a tank that is desuperheated by the compressor. The orange tank to the right is a buffer tank. The reason for the buffer tank is to keep the compressor from short cycling. The hardest thing you can do to this compressor is start it. When you start it, you want it to run for a long time, and when it is off, you want to keep it off for a long time. Figure 6-5 shows the details of desuperheating off of a compressor and utilizing that energy as a domestic hot water preheat. During cooling season, the system performs quite well. During heating system, there's very little residual heat left over to be utilized as a domestic hot water preheat. Figure 6-6 shows the use of the ground source heat pump system as a cooling medium. The buffer tank is obviously blue, showing cold water. The cold water is sent up through fan coil units where it recovers sensible and latent energy. It is important that all pipes connected to a chilled water system be vapor sealed and avoid the production of condensate around pumps, valves, etc. Shown in figure 6-8 is a 4-pipe heating and cooling system. The system is reminiscent of South Elizabeth. Essentially, you have the ability to be able to provide warm floors while also providing air conditioning to the consumer. Although this is a great feeling in the middle of the summer months, a person has to bear in mind that if you're dumping heat into the floors, it will end up in the air, and if it's in the air, it has to be rejected through the ground source heating system and a ground source cooling system, and you can't expect higher than normal loop temperatures at that point. Figure 7-1 shows a hybrid system. It utilizes the ground source heat pump for base loading of the heating needs of the building, and it also provides cooling if necessary. The staging of this system is essentially done by a control that once the water temperature is exhausted, and it's typically 115 degrees from the ground source heat pump, then the boiler turns on and picks up where the ground source heat pump left off. This is obviously showing some panel radiators, which are considered a high temperature application. It would be virtually impossible to utilize 115 degree Fahrenheit boiler water temperatures from the ground source heat pump to sustain comfort conditions if your only method of distribution is a steel panel radiator. This graphic demonstrates what happens to the fluid volume within the loop field system itself. It's exact opposite of what we typically see in a closed loop heating system. The reason being is that the polyethylene tubing has an extremely high coefficients of expansion and contraction. So as the system is in a situation where the loop is 50 degrees Fahrenheit, when it goes to 30 degrees Fahrenheit, the tubing shrinks and contracts. Consequently, the pressure goes up in the loop field system itself. Conversely, when the system is in the heating mode and the tubing expands, the pressure and the volume of fluid in the expansion tank contracts. It becomes less. This is important to understand if you happen to find yourself in the field looking at a ground source heat pump loop. Bear in mind, temperature of operation dictates pressure. Due to the fact that the supply water temperature has a maximum temperature of availability of 115 degrees Fahrenheit, the radiant floor heating system has to take this into consideration. Typically requires a higher density of tube, typically 6 to 8 inches on center if you're in concrete, or the use of warm board if you're in an elevated framed floor structure. This is very critical depending upon whether this is a hybrid system or a strict ground source heat pump system. If it is strict ground source heat pump, you must have high density tubing and very small centers in order to be able to get the fin effect that you need to get the BTUs per square foot per hour out of your radiant panel. If it is an upper frame floor, it's strongly recommended that the use of warm board be employed, which works quite well with the low approach water temperatures, and it also has the ability to be able to overcome any resistance values placed over the top of the heat emitting surface. This concludes the Advanced Hydronics Incorporated Air Source and Ground Source Heat Pump Basics. If you have any questions, feel free to contact me by either email m.etherton@advancedhydronics.com or give me a call on my cell phone. Thank you for learning, and continue to pay it forward.